Welcome to another series of seminar at the Center for Network Intelligence at DC and ISC. It's my pleasure to introduce today's speaker, Dr.Divyanshu Pandey, and we'll be speaking on enhancing millimeter wave radar field of view using multi-bounce action. Dr. Pandey received the BTech degree in Communication and Computer Engineering from the Indian Institute of Information Technology, Jaipur, and the MS degree in Electrical Engineering from the University of Minnesota, Twin Cities, USA in 2014, and the PhD degree in Electrical Engineering from McGill University, Montreal, Canada in 2022. Between 2011 and 2020, he worked as an assistant manager in the instrumentation team with HMEL, Bathinda, India. He also worked as a wireless system engineer with Marvel Semiconductors, USA from February 2015 to August 2017. He is a recipient of the Outstanding TA Award from the Faculty of Engineering at McGill University and the Base Student Paper Award at FICC 2021. He is currently a postdoctoral associate with the Department of Electrical and Computer Engineering at Rice University, Houston, USA, where he mentors graduate students in their research and teaches a course on modern communication theory. His research interests include wireless communication systems and networks, radar imaging, joint sensing and communication, information theory, and tensor algebra with application to communications at single. We request the audience to keep your microphone silent for the duration of the talk, except when asking questions. And for questions, feel free to unmute yourself and ask directly, or type them in the chat box. We'll review your question. Over to you, Dr. Pandey.
Thank you. Thank you, CNI seminar organizers, for hosting me today, and thank you for all the esteemed faculty members to be present here and allowing me this opportunity to share my ongoing research at Rice University on enhancing millimeter wave radar field of view using multi-bounce scattering. I would have gone through this slide, but she already did a very good job at summarizing everything that I've been doing so far. So in the interest of time, I'll skip through it. And I'll just introduce briefly what are my current research interests before going specifically detailed into this particular topic. Broadly speaking, I'm interested in all aspects of wireless communications and networking. To be more specific, the kind of problems that I'm looking for in past few years deal with all aspects of multi-domain and multi-function communications and sensing systems. What do I mean by these terms, multi-domain and multi-function? By multi-domain, inherently we know that the transmission and the reception in most modern communication systems spans across various domains, such as space, time, frequency being traditional ones, but then you can have delay, Doppler, users, code sequences. So we have different degrees of freedom across which we encode our data and decode. So the input and the output in any communication systems are inherently multidimensional. Hence, if they are represented using higher order tensors, the channel also becomes a higher order tensor. And that's one of the focus of my PhD thesis was. And that's what I mean by multi-domain communication systems. And by multi-function, I mean that gone are the days where we want to look at a base station or an access point as something which just communicates or does reliable transfer of bits. That's the bare minimum that we expect a communication system to do now. With sensing opportunities coming across, we expect our communication infrastructure to be able to do much more than just communicate. And that's what I mean by multifunction. And when I say all aspects, currently with my limited experience, I'm attacking these problems from all theoretical, algorithmic, and experimental point of view. To give you guys a slightly more specific idea about this, here I'm listing 3 specific highlighted projects that I'm doing. The first one is the tensor modeling of higher order channels and their channel capacity, which was mostly theoretical work done as part of my PhD thesis. Then RAM slicing based scheduling for massive MIMO, where we are looking at scheduling problem across time, frequency, and space within the RAM slicing framework, where different enterprises or different slices have different QoS constraints. This is more algorithmic work. And then multipath assisted wireless imaging, where we have part theory, part algorithm, and we are doing some experimental validation also right now, and which is exactly the focus of this talk today. Okay, so this was a brief glimpse of the kind of research problems that I'm currently working in and interested in. So before I proceed, here's a brief outline of the talk. First, I'm going to introduce the sensing opportunities in future networks, I think it's relevant, what are the major challenges associated with it, and what's our motivation for using multipath for imaging. Then I'll introduce the system model and describe my algorithm and system description, which we call Hydra, and the justification behind the name Hydra will be clear in a while. Followed by I'll highlight some experimental results and limitations of our current work, and what are my future research and teaching plans going forward. So let's talk about the sensing opportunity. When I talk about multifunction networks, I say that our communication network should do much more than just communicate. It should sense. Well, sensing has been around for quite some time. Radar is a technology as old as World War II, right? So we already have several automotive applications where your autonomous vehicles and for vehicular to everything network are using radars and lidars for sensing the environment. Different consumer technologies where almost all of our handheld devices have some sort of sensing ability right now, some radar or lidar installed on it. Different health and wellness features use radar technologies, use sensing. Weather radars have been common for quite some time. In fact, if you look at the spectrum, the communication part, much part of the communication spectrum has been used for various sensing opportunities already. So sensing as a use case or as an application, it's already established. People have been using it for quite some time. So what do I mean by the sensing opportunity? By that, I mean, now we want to do sensing using wireless communications infrastructure. And why now? Because wireless communications also has been around for quite some time. Why do we say that now we want to do sensing using the wireless communications infrastructure? There have been certain advances in wireless communications in past decade, most notably two of them being first massive MIMO, where now we are talking about base stations being equipped with hundreds of antennas. So we can actually convert every antenna into a pixel and then leverage the network scale of these base stations to be able to image with better resolution because of these large number of antennas. And now we are talking about transmission in higher bands, such as millimeter wave, terahertz. In US, now there are talks about FR3 bands, which is 7 to 24 gigahertz band. So these bands have much larger bandwidths available as opposed to the sub 6 gigahertz band, and hence we can get better resolution. In fact, in wireless imaging community, a self-imposed target is to achieve 1 degree angular resolution. In the sense, what I want my base station to be able to do is see everything around it. So if it can see with a very good resolution of 1 degree, it can actually map the scene around it using RF imaging. Such target could be minus 0.2 degree, but this is the baseline target resolution with where the research is trying to push towards this direction. And because of these advancements, there is hope that wireless communication infrastructure should be able to achieve this. Now, once a base station can see everything around it, what would it do with it? So, as I said, sensing on individual devices has been around for quite some time and we have been using it. Now we want network supported capabilities. We want network to be able to perform many functions by sensing the environment around it, not just individual devices. So if your base station can see everywhere around it, it opens door to certain applications such as factory automation, smart city, military applications, and vehicular network, tracking and locating people, environment sensing, all sorts of applications which could now be delegated for the base station or your access point to be doing. So our objective is that we want to enable networks and mobile devices to sense the world using communication spectrum, and then the use cases and the applications, they can be a variety of it. It's just limited by our own imagination. There was a recent 3GPP release in which they listed around 400 potential use cases or applications if base station could be able to sense the environment around it. So what do I mean in general by wireless sensing and imaging? Let me establish that. Here is a transmitter and receiving device. I'm putting here radar because radar is just one modality which does time of flight imaging, but the general principle can apply to any transceiver device. So let's say this transceiver is illuminating a scene The objective in wireless sensing and imaging is that we divide the scene into a set of pixels or voxels, and then we want to estimate the reflectivity coefficient of each of these pixels. The reflectivity coefficient of any pixel would depend on the physical properties and the characteristics of the object that lies in that particular physical location. And what are the major challenges in doing so? We can sense objects only in direct line of sight, and higher band signals are highly directional. So on one hand, we talked about that we want to switch to millimeter wave bands and terahertz band because they have much higher bandwidths available. But the higher you go in those bands, your signal transmission becomes more and more directional. So if it is more directional, then essentially your sensing field of view will get limited. In the sense, you can only sense what you illuminate. It's like a torch. If you put a torch to some place, you can only see the light where the torch is reflecting from. To give a simple example, suppose there's a radar system which has a beam transmission going something like this. I can sense things within this particular beam, but I cannot sense anything outside this beam. So my field of view of this radar is limited by the transmit beam pattern of this particular radar. To put it in a more practical example, suppose I want to map this car or image this car from a radar from the back side, I can get much information about the bumper of the car, but not much about the side of the car, because essentially I'm not illuminating that. So signal directionality limits my sensing field of view. That comes as a limitation as we keep on increasing, as we keep on going to the higher bands. Another major limitation or major challenge in doing that is the presence of multipath. Signal will bounce off multiple objects. It's inevitable because you have ambient objects, so you cannot get rid of multipath directly. And in line of sight processing, it leads to false detection or what we call ghosts that need to be suppressed. Let me explain what do I mean by ghost. Consider this example. If a radar wants to track this particular object, in this case, this human being, and there's an obstruction in front, it cannot see it directly from its line of sight. But let's say there's a wall and there's a reflected signal coming from the wall. This wall will act as a mirror, and if I'm only doing time of flight imaging, for all purposes, this radar will feel that the person is standing in this particular direction at this distance. This is called the so-called ghost problem, and a very classical problem where we need to identify where the ghosts are. And if you have information about the wall geometry, you can remap the ghost, but you need information about the wall beforehand. So we cannot detect behind occlusions, and we need to suppress any multipath information or try to identify it and remap it. But can we actually exploit multipath to assist us rather than obstruct in wireless imaging and sensing? That's the goal that we are going for. And what's our motivation for saying that, hey, let's make use of multipath? So let me establish the motivation behind why I think multipath can give us an extra information. First, as I said, multipath is unavoidable, but receive multipath components contain information about the objects they interact with and their location. For instance, if my radar is transmitting something directly at the door, I get a signal from the door reflected to the chair and coming back. So this particular reflected signal contains some information about at what distance there was an object and what kind of object it might have been. This information is contained in this multipath signal so far as I can extract it. So why waste it? And another way to say it, I can say that multipath provides a wider perspective or view of the scene, essentially creating a larger virtual aperture at the receiver. So I was able to see only in this direction, but because there's a reflected signal coming from that direction, essentially I have an eye in this direction as well. That's what multipath is doing to it. To depict it pictorially, think of it this way. Here's a transmit aperture, and here's, let's say, your scene. If this is the direct path and there's a multi-bounce path also, equivalently, this system is equivalent that there's a virtual aperture created because I'm now able to see in this particular direction as well. So with this, what we want to infer is that multipath is not a limitation. In fact, it's an opportunity. We should treat it as an information bearing entity and not a nuisance that needs to be suppressed. So let's exploit multipath and get rid of both the challenges that we are talking about. Multipath in itself will not remain a challenge, and can we use multipath to enhance the field of view and then combat the signal directionality challenge as well? So with that motivation set in mind, let me define the objective of what we want to do. Through this illustrative example, consider there's a millimeter wave radar here, and it could be any device, but I put millimeter wave radar here because our experiments were done using a millimeter wave radar, but the general principle applies for any other device. It is transmitting a transmit beam in certain direction and wants to sense objects in its so-called single bound zone. Something, a ray will go to the sofa, will be reflected back and will be received here. Based on time of flight imaging, radar should be able to tell that here's an object at this particular distance. That's my single bound sensing. But if I confine myself to only single bound sensing, this radar cannot see the trash can, the dining furniture, and another person may be entering the room. So our problem statement is, ultimately the signal that is going to the sofa, assuming sofa is a scatterer, it will scatter the signal in all the directions. So can I exploit this multi-bound scattering to get beyond field of view localization of objects in this radar signal processing pipeline? We call our approach Hydra. We recently published this paper in ACM OBCOM, and there's a provisional patent also filed for the same. The name Hydra comes from Greek mythology. I'm a huge mythology nerd. So in Greek mythology, you have a creature which has head in all the directions. So it can see in all the directions. So with multipath, that's what we are trying to achieve. There is ambient scattering around. That means essentially I have eyes everywhere. And that's why we named our approach Hydra. So what should Hydra do in principle? That I was able to detect using standard single bounce processing, but there was some reflected signal from the sofa to the chair and coming back to the radar. Can I exploit this signal to tell that there was an object at this particular location? This kind of path I'll call as double bounce path because it bounces through two objects. I can similarly go for triple bounce path where there can be multiple triple bounce paths from radar to sofa to trash can to back to sofa to radar. That's also a triple bounce path, and any reflection from this trash can to the wall and coming here is also a triple bounce path. So there can be multiple possible configurations of such triple bounce path, but our objective is to exploit them and be able to detect all these objects. Okay. Now, before I move further, I would take a quick pause here. If there are any concerns about if there are any questions about the motivation here, yes.
Spoke about reflection,
Right.
But what about other effects such as diffraction and stuff? Do they spoil the story?
So they do. So in our system model, when we develop, we make a rather tall assumption that each point in your scene is doing perfectly diffuse scattering. But in principle, depending on object property and object type, you can have diffuse scattering, specular scattering, a combination of thereof. So those are the limitations of the work. But the model we proposed was assuming each point is doing omnidirectional scattering, and we built an algorithm based on that. Experimentally, we noticed that even in case of specular object, it works decent, and I'll show some results on that. Yes, sir. You have a question?
Yeah. So you're focusing on millimeter wave, and already you have a significant attenuation in the long trip path that you get. Now you're looking at reflections from the red path and the green path, but will be significantly much weaker than
Much weaker.
So
Yes.
you separate those signals?
So as you'll see when I build my algorithm, we actually use this to our advantage, something similar to PD-NOMA, where we do successive interference cancellation. We make use of the fact that this signal will be strongest, double bonds will be comparatively weaker, triple bonds will be comparatively even more weaker. So we'll try to decode first and remove its effect and then try to decode the next one. That's the principle on which our algorithm is actually built. And I'll explain that in fair detail. Yeah.
Are they assuming that all the multipaths are resolving?
Sorry?
Are they assuming that all the multipaths that we get here are
resolvable? That's a great point. Not necessarily. We are relying on the receive beamforming abilities of this particular radar to be able to extract signal coming from any particular angle of arrival. So based on that, there will be cases where we will not be able to distinguish between two particular paths. Yeah. Yeah.
Since you are anyways considering multipath and reflected signals, why not have you considered looking at other transmitters and reflected signals bouncing off the objects?
Other transmitters
in the
in the vicinity. Yeah, so that would mean we'll have to have some sort of bistatic or multistatic configuration where the transmit and the receive devices are separate. Here, our initial experiment, our initial approach is using a monostatic device where transmit and receive antennas are co-located so that the receiver exactly knows what was transmitted. And that's how it actually does match filtering to detect this thing. But yes, a more broader application of this would be in a multi-static scenario where this guy transmits, there is some reflection, there's another guy which receives, and that should be able to tell based on these bounces that hey, there were some objects in the vicinity. But that's the future work that we are actually doing in bistatic and multi-static configurations. Okay, so with that, let me proceed. Let's first look at some prior work given our objective. Our objective is that we want to enhance the sensing field of view. Well, the simplest solution is put multiple radar units. You literally put an eye in all the directions. That's simplest, right? You'll get the entire solution. Of course, this means you're using thrice the hardware, 4 times the hardware. So it has more hardware complexity. Another thing is, if you have good beam scanning abilities, I'm saying my beam is very narrow, it's just pointing in this direction. Illumination is too strong. Let's have a transmit beam strategy where you are scanning the beam. Of course, you will illuminate the entire area and you'll get captures from all these places. So that also seems like a viable solution for increasing the sensing field of view, although it has more acquisition time. And radar mobility is the simple solution which forms the basis of the synthetic aperture radar concept in general. That you physically move your radar by either putting it on a board or physically moving it by yourself from this location, that location. From each location, you capture information. All these are viable methods. But you will see once I'm developing our approach, Hydra doesn't come in competition with any of them. It's a complementary technique to all of them. You can have this and have Hydra as an add-on feature. Have this, have Hydra as an add-on feature. It will enhance field of view further. And one of the problems that I was earlier talking about, that it creates ghosts. In literature, most of the times it's being handled that you can do ghost remapping, provided that you have information of the wall to begin with. If you know exactly the scene geometry to begin with, then you can use this to remap the ghost by identifying the ghost, but this requires prior knowledge of the environment. So these all methods, while all good, they have either higher hardware complexity, higher measurement acquisition time, and requires prior knowledge of the scene. And Hydra, as I said, can be used in a complementary way to all of them, where we use a single millimeter wave MIMO radar. In a single capture, we are actually trying to image the entire scene without any knowledge about the scene beforehand. Okay. So let me now come to building our algorithm. But in order to build our algorithm, first let me introduce the system model that we have. The received signal in an R cross T MIMO system, where R is the number of receive antennas, T is the number of transmit antennas, can be specified in this manner, where we are summation over all the L, all the multipath L. Let me walk you through the components here. Let xt be the complex signal that your transmitter is transmitting, and W represents the beamforming waves of the transmitter. ARX is the receive steering vector corresponding to a particular angle of arrival, and ATX is the transmit steering vector corresponding to a specific angle of departure. And alpha and tau are the attenuation of path L and the time delay of path L. This is the generic system model for any path. Now, because we are talking about considering single, double, triple, and higher order bounce path, let's specialize this system model for these specific bounces. Let's write this for a single bounce. Supposing we have only single bounce signal, and I didn't mention, but I'm of course ignoring the presence of noise here. The system model is in the absence of noise. Suppose you have only single bounce path. Here's a radar. Here's a point P, a pixel P in the scene. You send a signal and you receive it back. So how would your system model be modified for only single bounce path? Essentially, your angle of arrival and angle of departure will be same. Your delay will just be the round trip delay to location P, assuming radar is at the origin. Then this just denotes the Frobenius norm or the Euclidean distance. And alpha L will denote the path attenuation due to path loss and the reflectivity of this point P. Right? So if I were to write this system model, assuming that only single bounce path exists, there is no double bounce, there is no triple bounce. It would be written something like this, that I'm summing over all the pixels P, where P denotes the set of pixels in my scene, and I have dependence only on the theta, which is the angle between the radar and the point P. Now, I can match filter with the received signal xt because transmitter and receiver are co-located. Receiver exactly knows what xt was. I can match filter with xt and represent the received signal in frequency domain. The delay term will come in exponential, and you will have a frequency domain representation, which will be given something like this. The goal is now to estimate this sigma p for all the points in the scene based on observing this received signal y. If there is a non-zero sigma p, we say that it indicates the presence of an object at the scene. If it is zero, that means there was no object at that particular location. While, as you will see later on in our work, we ended up just converting the problem to detecting either the presence of an object or the absence of an object. But if this were successful in its 100% sense, by looking at the value of sigma p, we should be able to tell material properties and other stuff also, right? But here the goal is we want to estimate sigma p, and one of the standard methods in literature that exists to do that, called backward projection or adjoint inversion, where essentially what you do is you receive beamform to locations p, and you match filter to this transmit steering vector and transmit beamforming waves, and account for the path length between the radar and the point P. And you average over all possible frequencies over which you have captured your signal. So this method is called adjoint inversion or backward projection, and has been used for in computational imaging in several places. What we want to do is we want to extend this to double bounce, triple bounce, and higher order bounce as well. So now, can I mod? Sorry, yeah.
Why does it work?
Sorry.
Why does it work?
So it's essentially you're countering the effect of everything else. So this is exponential minus j, so you counter the effect by exponential j omega c. So you see, this will keep cancelling out every other term. Yeah.
So how is this different from received beamforming? So the beam scanning, you can only do match filtering to one of the locations.
One of the locations. This is exactly what this is match filtering to one specific location. I knew exactly what signal I transmitted. So this we are doing over, this is for a particular location point in the grid P, and you do it for all P's. So for all P, sorry?
You're doing beam scanning.
Yeah, so receive beam scanning. So receive beam scanning is not literally scanning anything, because once you receive something on the receive aperture, that's what you have received. But digitally, through receive beamforming, you can extract the signal coming from theta1, theta2, theta3, and so on and so forth. So you extract from all these different theta directions and then perform this operation.
But you have multiple scatterers, right? You will not do match filtering at the receiver.
Sorry, say that again.
Match filtering at the receiver is good if you have one scattering, point scattering. You have multiple point scatters, and you have reflections that are superimposed, then you will not be able to suppress that with the match filter.
Yes, so that's why this is what we are doing point-wise. We are doing for a particular pixel value P. This is for one particular point in the grid from which we are assuming there's a single bounce reflection, and we are just doing match filtering in that particular direction. And yes, we need to do it for all sigma P. Essentially, what you are receiving is a sum of all of them. But I'm saying in angular domain, I have, depending on my number of receive antennas, I have this resolvability that in angular domain, I can separate the signal coming from a given theta from another theta from another theta.
Condition which will give you this. Otherwise, I cannot do it.
So you should do either zero. I mean, you should do either zero forcing receive.
Yeah. So what we are doing here is we are doing, when I say we are doing point-wise operation. So here's the data. Let me show the figure that is. Look at this configuration is what we are actually doing, and we are doing it for all the points P individually. So individually, if I get some reflection from this point, of course I will not get any reflection from any point beyond this. That's the limitation of the system model. That's one of the limitation in the system multiplier. But if this is the point from which I'm getting reflection, I should be able to, and if I can resolve this particular angle theta, I should be able to estimate the sigma hat p using this averaging over all the frequencies that I've received for one particular pixel value p at a time. And then I can do it for the next p and the next next theta and next theta and next theta.
When you written that y or the check sign,
Yeah.
it's sum for all points, correct?
Yes, it is sum for all
When you
points.
start doing match filtering, you're actually gonna apply to y and right, not to just one p. So that multiplication should be able to suppress everything else other point to 0 and just take over this p, right? That's somehow that's what is happening. Otherwise, you will actually get sum over all points p, right?
Yeah, okay. This is because summation over all other
Yes.
points p,
Yes.
and this is just for a single
so you
particular
multiply
p.
that, right? So
Yeah, and that how we get that is that because we are actually multiplying it with a particular theta p, and we are just extracting the signal in that particular theta p. And okay, now I get it what you were asking for. And this, when you your receive beamform, when I say your receive beamform to location is p, that means at this time, if you the signal coming from any other p prime location with this will be 0. So you are only receive beamforming towards a specific location. You are only extracting the signal coming from that particular location.
but then you've got a
Sorry.
just want to make sure I get it. You've got a beam width. Now, within you're essentially assuming literally a chronicle delta beam width. So nothing else around it. If you've got a beam width, you've essentially got a sinc function type decay around it. So what is your beam width assumption?
So in this case, for single bond processing, we have 2-degree separation for each theta p. So there will be, yes, there will be, it's not exactly pencil beam. So we don't have that sharp granularity that we exactly getting at 30 degree or something like that. But you process it at a granularity of 2 degrees for single bond processing, we are able to resolve it. And that is a function of the number of receive antennas that we have at the board that we are using. Is it okay? Any other concern? Okay. So now let's try to extend it to double bounce. Now what's happening is we are transmit beamforming towards the position P, and we are receive beamforming towards another position P prime, where we assume that a signal scatters off from the point P to P prime and then is received at my receive aperture. Now, assuming that there's only double bounce path, I can write my double bounce path in this particular fashion, where the sigma coefficient is now the combined effect of reflectivity of P prime due to reflection from point P. My receive beamforming is from point P prime, my transmit beamforming is towards P, and the delay will now depend on the entire distance traversed between radar P and P prime. I can apply adjoint inversion to this also by essentially, in order to find the estimate of the double bounce reflectivity at location P prime due to reflection from point P, and what we do is we transmit beamform towards P, receive beamform towards P prime, and compensate for the double bounce path length d distance between P and P prime. So analogous to single bounce, we can extend it to double bounce also.
Where do you get the distance between them or the time between?
This distance, so because we'll solve it for each P and P prime, and we know the radar location, so we know these distance values. So we'll solve it for each P and each P prime. And if this will come out to be 0, we'll say there was no object. If this is non-zero, means there was an object there. Okay. Continuing with this, we can actually model triple and higher bounds also. So you can have that your transmit beamforming towards P, receive beamforming towards P prime, but intermediate, the reflection did not directly go there, went through some other point, P double prime in between. So you can have a triple bounce model written somewhat like this. You can apply adjoint inversion to the triple bounce also and try to get an estimate of sigma hat, which is a combined effect of P double prime and P prime. Now, theoretically speaking, I can generalize it to nth bounds. Of course, theoretically speaking, in practice, we'll see that the power really diminishes significantly after triple bounds, that it becomes, at least experimentally observed, it became meaningless to do anything further. But theoretically, I can extend it to nth bounds, and I can have an nth bounds adjoint inversion also. Now, in order to build an algorithm from this, our first observation was through a toy experiment that we created, and I'll go into details of our experimental setup later on. But here I'm trying to make the point about diminishing power of multi-bounce path. That if there's a radar which is transmitting a signal towards a particular, let's say, object, in this case C1, and there are C2, C3 objects placed in the environment, and I orchestrate this environment such that I exactly know what are the possibilities for a single bounce path, for a double bounce path, for a triple bounce path, and so on and so forth. If I look at the received signal power, this is the kind of received signal strength that I see. Compared to single bounce and double bounce, there's a difference of around 25 dB. From double bounce to triple bounce, there was a difference of around 15-20 dB. And beyond that, fourth bounce and other bounce, they were almost at a clutter level. Right? So experimentally, our observation said that beyond triple bounce, the power is so low. Even for triple bounce in certain cases, the power is not good enough to extract it. But clearly beyond triple bounce, we are almost at the clutter level. However, single bounce power dominates. So I can do my single bounce processing, assuming there's no double bounce or triple bounce. I can just extract signal based on that. Once I have my single bounce estimate done, I can remove the impact of my single bounce and then do my double bounce processing, something similar to what we do in successive interference cancellation, where you first decode the highest power signal and then you decode the second high power signal, and so on and so forth. So, and that forms the basis, the main crux of our idea, which is sequential detection and localization. Yeah.
Can you just comment on the false alarm probability setting? How would you set it? I see two numbers, 5% and 20%.
Yeah.
But
So
in general, like how would you play with that for your setup?
So in this case, we use CFAR detectors, constant false alarm detectors, where we are setting these probabilities based on target to clutter ratio. We are setting if the sigma hat estimated is above 0.5 times the median value that I get the sigma estimate in its neighborhood. Based on that, we are setting these values. So essentially, we get these on estimation, we get these sigma hat values, let's say, which are continuous numbers. We threshold them to decide whether there was an object or there was not an object.
No, the PFA will determine your threshold. I get that.
Yeah.
But how do you choose PFA? That's something you have to kind of decide before you run the algorithm. 5%, 20%. How do you get that number?
So we chose that actually empirically. We experimentally played around with the number, what threshold we should pick to get this particular value. So we chose that empirically to be 0.5 times the median value around the grid. So why we chose 0.5? That was actually an empirical observation. So the main idea that we have behind our approach, sequential detection and localization, supposing here's a radar, it wants, and there are objects kept in 0.1, 0.2, 0.3, and one of the tall assumptions that we are making is that there is diffuse scatter, that is every point scatters in all the directions. Suppose the transmit beam illuminates only 0.1 and does not illuminate 0.2 and 0.3. So I can estimate sigma hat p for all the points in this range, where I'll get something non-zero for the grid position at 0.1 using my single bounce processing, assuming that there is no double bounce, triple bounce, everything is zero. The resolution of this will depend on the resolution capabilities of your radar board, how many transmit and receive antennas it has. Based on that, this will determine the resolution, which in our case was around 2 degrees. But now during double bounce processing, this component is known because we have already estimated it. So we estimate sigma hat p for all points in the double bounce region by first removing the effect of YSB and then assuming that everything triple bounce and higher goes to 0. Yeah.
On the previous slide, so what is the type of reflector that you're assuming? So C1, C2, I guess you're assuming these are scatterers with isotropic RCS.
Sorry?
Are these scatterers with isotropic RCS?
Yes. So the assumption is the omnidirectional scattering, right? But in our experiment, those cylinders were aluminum coated, designed particularly to create that way. Those are toy experiment. But then we ended up doing experiment with human beings and some furnitures. So we did experiment with a range of objects. With certain, you were actually getting good performance. Certain objects, depending on their specularity, you were not getting good performance. So, but this here assumes that each point can diffuse only in an omnidirectional way. Okay, so we estimate sigma hat p for my double bounce processing. Now the resolution of the double bounce is determined only by the number of receive antennas and not the transmit antennas. So it will be slightly poorer than resolution in my single bounce. Once I've done that, now for triple bounce processing, I know the single bounce and the double bounce thing. I can estimate sigma hat p for triple bounce. However, sigma hat p when I'm estimating for triple bounce depends on the entire distance between radar to point P to P double prime, P prime, and radar. And point P prime could be anywhere. So that's why if you want to estimate this, we'll only get an arc because there will be different P double primes corresponding to which we'll get the same value. In order to resolve it from this arc, what we need to do is we need to exploit multiple such reflections, get multiple those arcs, and look at their intersection. That is how you localize a triple bounce object. So to put the entire algorithm in a system framework, we need to know the transmit beam pattern of our radar because that determines the single bound zone. We collect our radar data cube where these collect measurements across this frequency domain. And then we do this multi-bounce processing where first we do single bounce adjoint inversion, apply a CFAR detector, which is a constant false alarm detector, to basically threshold and determine whether there is an object or not an object. And then we detect in region S1, then give this as an input to second bounce processing, continue the process till for 3 bounce. Theoretically speaking, you can continue the process for nth bounce also. However, you can imply some stopping criteria after which you can spit out your sensing output. And the stopping criteria for us was after triple bounce, the power of was so low that we were almost actually trying to decode clutter, right? So I'll now go over my experimental setup and results, but are there any questions on the algorithm? Yeah.
You assume that you know that you have one bound, second bound, third bound, till nth bound, all the possibilities are there till nth bound in your algorithm. Suppose first bound is there, third is there, second is not there. And
So
performance degradation you get, or it doesn't matter.
Okay, that's a good point. So if there is no single bounce object, then the algorithm itself doesn't work. Because if there's no single bounce object, there's nothing to scatter the signal, right? I'm just eliminating a vacuum. So there's no scattering. However, if there's no double bounce, we can still do triple bounce processing. Ultimately, in double bounce processing, you'll get a bunch of zeros. All sigma hat will be estimated to be zeros. You can still do triple bounce processing because, for example, a simple scenario behind the radar. If I keep the radar here, I transmit a signal through the wall. Signal goes to the wall, comes back, looks at me, goes back to the wall, and comes here. That's a standard triple bounce path behind the radar or behind an occlusion. And those can be processed. For that, you don't need double bounce step. But yeah, for single bounce, you need something in single bounce for sure.
The sigma thing you mentioned, it's a real positive real number.
It's a complex number. We end up estimating its magnitude. It's a complex number, which is the reflectivity coefficient of the particular object. Yeah.
How much does the noise affect all of this?
So the noise will actually
Noise and the estimation error propagation.
yes. So in terms of what noise does is, okay, I went too far, I think. Sorry, I went too far. The noise will actually raise your noise floor, clutter power. So essentially, maybe your triple, because you might get some reflections out of, we are doing everything in azimuth, right? Azimuth plane. You can get some reflections out of the surface also. So those things will enhance your noise, and essentially your noise and clutter power will increase, and you might not be able to distinguish even triple bound signal. That's definitely happened. And as per error propagation, definitely, because if it's sequential detection, SM will get propagated. I don't have the slide here, but in our paper, we theoretically show that how error propagation in single bound will affect double bounds and so on and so forth. But there will be error propagation for sure. If you end up making mistake in single bounds, we'll end up detecting, enhancing the error in double bounds processing. So our experimental setup, we did our experiments with this FMCW MIMO radar, which has 12 transmit and 16 receive antennas. This is an off-the-shelf radar bought from Texas Instrument. It claims to be having a 1.4 degree line of sight angular resolution. The best we could get with a very strategic object was around 2 degrees or so. And it operates at 77 gigahertz band with 2.5 gigahertz frequency and range resolution of 6 centimeter. And these are the different kind of scenes in which we tested our experiments. indoor hall in rice, outdoor environment, some terrace environment, and some U-shaped staircases. So let me first qualitatively show a few results. So here's the radar transmitting a beam, and in this radar we have transmit beam forming abilities that I can span from minus 30 degree to 30 degree, and I can decide in which angle I want to transmit. So if I transmit towards human 1 to single bonds processing, I can detect human 1, but I cannot detect anything about human 2 because I'm only doing single bonds processing in the entire scene. If I do double bonds processing also, I can actually localize outside the transmit beam because there would be a signal coming from the white t-shirt guy to the yellow t-shirt guy and back to the radar. And that I can exploit to localize outside the transmit beam. For the triple bounce case, consider the cylinder example. I'm only showing the triple bounce processing where you will have multiple these arcs created due to multiple reflections, and from the intersection of those, you should be able to localize behind the radar using triple bounce processing. In order to have a more clear view of how actually sensing field of view sensing field of view is enhanced, let's look at this specific example. Interesting U-shaped staircase. Exactly what we needed was somehow there in Rice University. So we kept a radar here. It is transmitting a beam here, and a human travels in this entire path. And we want to localize this human. So clearly, if you do only single bounce processing, you can detect the human in its illumination zone and right in front of the radar. If you do single plus double bounce both, you can actually get localization, better localization error up to half of the staircase because double bounce path exists till this zone. And if you do single plus double plus triple, you can actually cover the entire hallway, entire U-shaped staircase because you are able to extract triple bounce signals to be able to localize these, localize the human. Now, in our paper, we have some more results and benchmarking also, but here I'll present maybe one more result, which is a quantitative result we have averaging over hundreds of experiments that we did in several scenarios, that the localization error, beyond field of view localization error, can be improved up to 2x if you just do the one extra step of double bounce processing. And if you do the triple bounce processing also, it can improve till 10x. However, this result should be taken with this consideration that our experiments were so designed that we had certain cases where there are objects behind the radar also, right? So the scene was created in such a way such that triple bounce actually shows some benefit. But the idea is to show that in specific scenes, double bounce and triple bounce processing should be able to help us.
What does this chart mean? Single bounce processing?
Sorry?
Single bounce processing for an object that is right in front of the radar.
Yeah.
So why is the error there rather than the error in...
So that's what I said. When we are doing single bounce processing, we are also considering those cases where I'm trying to do single bounce processing to detect an object which is not in its illumination zone, right? But if you just do double bounce, you can remove that error, and that's what I mean. So limitations, clearly the work has certain limitations. First, resolving between multiple beyond field of view targets and occlusions. Our experiments as initial proof of concept were designed with very orchestrated environments, so to say. We put simplistic objects, humans, sometimes table, chair, and these kind of things, but one or two objects at a time. We didn't consider a very cluttered scene, something like maybe this classroom. Then we assumed diffuse scattering in our system modeling. Even though when we are doing experiments, we did experiment with whiteboards and reflective smart surface, reflective surfaces, which would be very specular. But the model doesn't consider them. Experimentally, in certain configuration, those things will work fine. In certain configurations, those things will not work fine. But the model itself doesn't consider that. And then our experiments are limited to only azimuth plane. We did not consider elevation. And something which somebody mentioned here, what if there is insufficient or no detections in single bounce? That just means a hydrisotropic thing, because there's no single bounce, you cannot do any double triple bounce to begin with. But of course, all these limitations decides our next steps, what exactly we are going to do. So first, we need to consider more cluttered scene with multiple objects. This is something which is right now we are planning to do as next step. We want to account for specularity of objects in the scene by considering the surface, normal, and their specific properties also. We want to extend to 3D localization, including elevation. And in order to combat this particular challenge, what if there is no single bounce object to begin with? We want to look at intelligent reflector design and placement to deliberately induce multipath for increasing field of view. So far, we were talking about using reflections from ambient objects in an opportunistic way if they exist. But once we have established that you can actually use multipounds to enhance your field of view, why not we place reflectors intelligently in our environment such that a single radar is able to capture wider area? That's what we are now looking at. Are there any questions? Yeah.
Can you go to that double bounce formula again? It will be
Double bounce formula. Okay.
double bounce.
Okay.
Yeah, let's say you have said that that sigma p dash is you have taken it to be the magnitude, right?
Yeah, absolute value is.
Yeah. So there are many such combinations that you are coming over, right? Now, if you don't, and they can have completely different phase shifts because it's a complex number, right? So they can add up constructively also, destructively also. You never know. So don't you think you should include that?
So what we are doing is we are estimating for one symbol at a time. We are not estimating the sum of all sigma p's. We are estimating a particular sigma p. For a particular sigma p, we are estimating that at a time, right? And we are actually estimating a complex number. It's when you're plotting it, we are not such much right now analyzing the phase of it. We are only looking at magnitude. But eventually, yes, we want to look at the phase because with the phase value, we should be able to tell better what kind of object it is, what phase shift it caused, right? But here we are doing it individually, point by point.
Two questions.
Yeah.
Can you go to this picture where you had a stage?
Okay. Yeah.
So, how do you process here? You're focusing towards the beam that you displayed in the picture, but then the received beam forward is focused towards, say, the last location.
In this entire blue area, that's where we are receiving beam forming from all these areas. This blue arc. So we do background subtraction as first step, which I didn't mention because there'll be reflections from staircase and everything. So we do background subtraction first. Then transmit beamform is this light blue thing, and we receive beamforming in this entire range.
And so, how does it fit the reflection from the last point?
From the last point, so
Yes.
one, yes, 1, 2, this one here 3, and from here. So you are transmit beamforming because this triple bounce, right? 1, 2, 3, 4, like that. So if I could draw it here. So this is the staircase. This is where you keep your radar. This is where the human is standing. So the triple bounce path exists in this manner.
And what is the surface that really is concrete?
Surface, this is drywall. Drywall. The surface, yeah, it's a drywall. Okay, so this is where triple bounce exists, and then double bounce will exist something like this, and single bounce will exist like this.
So there is something called coded aperture radar.
Sorry?
Coded aperture radar.
Okay.
Where instead of transmitting beam in a particular direction, you spread the beam. So, for example, you could use random beams, but with known beam patterns.
Right.
So, why should not one use that traditional method rather than focusing in one direction with putting all the energy in that?
So one could definitely do that, and that's what I said. This method could be complementary to that. You can, if I understood your question correctly, you mean that the transmit beam abilities itself is much wider.
I mean, people have done this with compressive sensing.
Right.
More recently and traditionally, where you use random beam patterns, but with known beams that go off the transmit.
Correct.
So you spread the energy everywhere and then pick up again energy from different locations that you can decompose.
Yes, that is correct. And in an open environment, that is possible. That your beam scanning abilities itself allows you to illuminate the entire scene. But somewhere, let's say you have an obstruction. So for this particular instance, I can't think of any beam pattern, any transmit beam pattern which will directly illuminate the point here because of this obstruction right here.
Oh, you still receive the multipath.
Yeah, you receive beamforming is from the reflected signal. You're getting the reflected signal from the receive beamforming. But in order to illuminate that particular point from transmit beamforming itself, that point has to be in front of the radar and not obstructed by any particular object, not occluded in something, right? So if you could actually do beam scanning to enhance, that's all the way good. We should do that. And on top of that, you can add Hydra processing to even include those points which were occluded even with this expanded beam.
The channel would be reciprocal. Right? If you're able to pick up that signal with the receiver, it should also be able to illuminate that.
Sorry, can you say that again?
Be reciprocal.
Okay.
If you're able to pick that received signal through this multipath, we should also be able to illuminate the transmit.
So that's what is happening. It is getting illuminated, but through a reflection. So there's a reflection happening, right? So even in double bounce, triple bounce, all this processing. Yes.
And
So that's happening in every experiment that I'm doing. Double bounce, triple bounce points are getting illuminated by the transmit beam, but not directly, not via single bounce. They are being illuminated via multiple bounce. That's what is precisely happening actually. So we are not saying that the double bounce, triple bounce points did not get illuminated. Without getting illuminated, we will not be able to do anything about it. Because if a reflection is coming from them, that means there was some incident signal to that. But the incident signal is not line of sight, it's not direct. It's coming through a bounce. Okay. So I think more details are there in our paper. I'll share a link for our paper soon. But with this in mind, let's talk about, can we do more than just localize, and how much time do I have more? I'll adapt accordingly.
1 minute.
Okay. So, okay, I'll quickly go over it. Can we do more than just localize? I talked about we want to do wireless sensing and imaging and end up doing only localization because experimentally that's all we can do. But two other interesting things we are doing is, one is velocity estimation. A radar can estimate the velocity of a moving object, but only the radial velocity, not the tangential velocity. But if you think carefully, if there's a static pillar there and there's a double bound signal, with respect to the eye that is the double bound signal, the tangential velocity is the radial velocity. So I can exploit the double bounce path to estimate my tangential velocity, the single bounce to get radial velocity, and hence get a full velocity vector estimation. And this is one of the work which we are currently doing in collaboration with UCSD, and some initial results we have presented in IEEE CISA in last year. And another thing that we're looking at is non-line of sight vital sign estimation. That is, we just don't want to say that, hey, there's an object, there's a person. We want to be able to tell his breathing rate or his heart rate. And this has application in disaster search and rescue scenarios. This is an ongoing project with IIT Kanpur right now, where some of our initial results have been accepted in ICAST 2025. And I know I have just 1 minute, so should I go on? Can I get 2 more minutes to maybe talk about what my future research plans are? Okay. So my future research plan, in the immediate future, I want to look at opportunistic sensing using communication waveforms, because communication waveforms are anyway scattering around us all the time. So can my Wi-Fi access point map